Hello. We are Group 28, the Autonomous Turtlebot Swarm, and I'll introduce our members and then we'll get into the topic of our project. So I'm Patrick. I worked on creating the simulation and helping get all of the different parts working together.
I'm Mark, and I worked on the custom object detection part of the project.
I'm Nathanael, and I worked on the pathfinding.
I'm Pablo, and I also worked on object detection.
I'm Noah, and I worked on the navigation.
Our project's objective is to create a fully autonomous robot swarm of 4 to 5 robots that communicate together and search an environment with time constraints to find an object. Our solution to this problem is using the latest computer vision and pathfinding algorithms to search and disable a predetermined target.
So the requirements for design of this project, first off, our simulation environment, it will be ran in gazebo with the dimensions of 400 by 400 by 400, and it contains obstacles. This environment, this map is a city, which you'll see later on. We'll have a swarm of 4 to 5 turtle bots that use interagent communication using ROS, and the pathfinding will be done using SLAM for the mapping, and once the map has been created, it uses a grid search to search throughout the mapped environment. And lastly, the object detection will be done with YOLO to recognize the target. And for our requirements for the target acquisition, it must have a bounding box that accurately surrounds the target and a confidence of at least 0.8. Our simulation environment is Gazebo 9.0, which runs on Ubuntu 20.04. The turtlebots that we're using are the Turtlebot 3 Waffle, and this is all on the ROS Noetic version.
All right, so for target detection, we trained and implemented YOLO v3 as our custom object detector. We had to collect custom data and run that through Collab to train this to get the weights. And then it runs on an average of about 30 FPS in the simulation. Originally, it was extremely lower than that, but Pablo will touch on that later. Once the turtlebot has a confidence score of at least 0.3 on the target, it will move closer until a confidence score of 0.8 or greater is reached. If that does not happen, the turtlebot will continue on its predetermined path to the next waypoint.
So for our pathfinding algorithm, the turtlebots use a map of the environment to localize themselves, figure out where they are. As they head through the environment, they're going to map the surroundings and perform collision avoidance. And then at runtime, we're going to generate a series of waypoints, and the entire area that we're searching the target for will be split into a separate area for each turtlebot, and they will then perform a grid search on it. Once the turtlebot reaches a waypoint, it'll move on to the next one, and if it can't reach one, it'll just go to the next one. So the entire area will be searched, and the simulation will end with either a success or a fail. For our test plan, we've already tested the object detector on a test set, and we reached 0.9 of mean average precision. We iterated over different implementations of the pathfinding, and we're going to find the best variables to make sure the turtlebots don't cast a net that's too wide or too thin based off of performance. And we're going to work with different environments to see if there's any problems with the turtlebots finding their target.
So now we'll talk about the challenges faced working on this project and the lessons learned. So I'll start with the simulation. Setting up the simulation was fairly difficult as there are a wide variety of different versions of ROS, which is the robot operating system used to control the turtlebots. A lot of packages are out there, but they lack documentation, and most of them are outdated and are not supported anymore. Pablo will talk about the object detection challenges.
So as for object detection, one of the first challenges we faced was when we had to change the model of the target, which required us to regather and retrain a lot of data, about 1,000 images. We also ran into the problem that the turtlebot waffles only came with, the cameras did not have a 360-degree field of view. So we figured out how to modify the URDF files and the gazebo files to attach more cameras to the turtlebots. Also, implementing YOLO version 3, although fairly straightforward on our virtual online ROS check, was rather difficult on a local system, but we did manage to install it into Patrick's machine. And lastly, originally the object detection had very low FPS. We installed CUDA to make use of the GPU, and now we get about 30 frames per second.
So for pathfinding, throughout the project, we were trying to use a SLAM algorithm that didn't depend on the GPS. Because of issues we had with that, we moved on to one that works on a mapped environment. And then a big issue we had was setting up multiple drones on our implementation. We found out that that's actually depreciated, so we're working on workarounds for that.
So for the broader impacts, our project is an intelligent search and disable system. One big and positive impact is that it minimizes human life risk, because we're sending robots to search as opposed to humans into areas that are potentially dangerous. Secondly, it's also can be modified and applied to be a lightweight search and rescue system, where the turtlebot can search for people in danger and help in those situations. Of course, it's no understatement to say that technology needs to be handled carefully and can be dangerous if misused.
Okay, so that's an overview of our project, and now we will provide a short demo of a turtlebot using the technologies we discussed to navigate through an environment. So this is the environment. As stated before, it's an urban environment with many obstacles like trees and lampposts. Here's our turtlebot, which is the robot that is moving through the environment and will be searching for different objects. Currently, we are still in the process of implementing custom object detection for a specific target. So for this demo, we will be using a public data set that recognizes a wide variety of objects in the simulation. So all of this is being run through on Linux 20.04, the latest version of Linux. And that first window shown was the simulation window. This window is the mapped out environment with the turtlebot localized. This next program is the waypoints program that we wrote to give the turtlebot different waypoints to explore throughout the environment. And as you can see, once it starts, the turtlebot starts moving to the designated waypoint. And the last thing that we start is the object detection, which will give us a window of what the turtlebot sees, as well as any objects that the turtlebot is detecting. So as you can see in this new window, it is recognizing classes from the public dataset, the COCO dataset. In this case, it's recognizing a car or a truck, and all while it's moving, it's pathfinding throughout the environment to the list of waypoints that we provide. And that's about it. Thanks for watching.